Hi students, now today class discuss about the divisional algorithm basic theorems. Okay, before going with that, last class discuss about the divisional algorithm problems. Now today class discuss about the divisional algorithm, one of the basic theorems. Okay, see the theorem statement, first one. Theorem statement: every odd integer is of the form. Every odd integer is of the form 4k plus 1 or 4k plus 3. Every odd integer is of the form 4k plus 1. Every odd integer is of 4k plus 1 or 4k plus 3. Okay. First, write the proof. Now here sentence is every odd integer. Every odd integer means generally you can mathematics write it as general unknown value is n. So write it as let n be odd integer. Let n be odd integer. Now after that one, by applying by division algorithm, concept, n is of the form. Here every odd integer is of the form 4k plus 1 or 4k plus 3. This is the only first term or third term odd integer. But you have by division algorithm write it the general term. So based on that one, write it the general term is of the form 4k plus n. The general term notation is 4k plus n, and write it as 4k plus r. Okay, and then 4k plus r. Here r is nothing but general all the values 0, 1, 2, etc. all the values 0, 1, 2. Now see the statement. This is the division algorithm general statement is of the form 4k plus r, but we have to prove that every odd integer only. For r, the r values 0, 1, 2, 3, etc. all the values, that values you can write it as only odd numbers. So based on that the statement, here r not equal to 0, r 2, sorry, r2 is not odd numbers. So write it as hence n is of the form, hence n is of the form. Based on the division algorithm, generally you can write r equals 0, 1, 2, 3, etc. But your statement you can write as only odd integer numbers. So take it only based on 0, 1, 2, 3, write it as only odd numbers 1, 3, 5, etc. type. But we have to prove only 4k plus 1 and 4k plus 3 times. So hence by the division algorithm, n is of the form, write it as 4k plus 1 or 4k plus 3. Only write it as general statement. Based on that division algorithm, write it as 4k plus 1 or 4k plus 3. So finally write every odd integer is of the form 4k plus 1 or 4k plus. This is one of the basic theorem. Come to the second basic theorem. This is not a basic theorem also, that is the problem also considered. So write it as show that, second problem, show that show that 2n cube plus 3n square plus 1 is divisible by 6. Is divisible by 6. So you have to prove, not the problem also, consider as the problem or theorem. Show that 2n cube plus 3n square plus n is divisible by 6. This statement you have to prove by induction principle method. You have to find out the solution. Okay, write solution. By induction principle, generally induction principle method generally notation is p of x, p of z or something. So write it as here p of, the variable is p of n. So write it as p of n equal to 2n cube plus 3n square plus n. 2n cube plus 3n square plus 1 plus n. Here for n equal to p of n equal to 2n cube plus 3n square plus n. Now induction principle method is you are substituting 0, 1, 2, 3 etc. nth term. First you have to check it n equal to 0. So p of 0. So we get the answer is, so put n equal to 0, we get the answer is 0 is divisible by 6. Is divisible by 6. Now check it 1, 2, 3 etc. value, but you have to consider only nth term only, other kth term only you can check it, the solution will be true and proof only. So right. So if you write the induction method, assume that p of k equal to 2k cube 3k square plus k. Put replacing n equal to k, 2k cube plus 3k square plus k is divisible by 6. Assumption is divisible by 6 is divisible by 6 assumption. Now write it as, check it each nth term value. So write, let write it as 2k cube plus 3k square plus k 2k cube plus 3k square plus k equal to, here divisible by the term is divisible by 6. So write it as equal to the term equal to 6m. The m is any integer value. So the term equal to 6m. So you have to prove p of k plus 1 is true na, your statement will be true. K plus 1 is true na, your statement will be true. So replacing above term k equal to k plus 1. So we get 2 into k plus 1 whole cube, 3 into k plus 1 the whole square plus k plus 1 equal to 6. So that equal to, applying a plus b the whole cube, a plus b the whole square expansion, we get the solution. So first write it as a plus b the whole cube, a cube plus 3a square b plus 3ab square. So 2 into k cube, so 3k square plus 3k plus 1. Second term a plus b the whole square, a plus b the whole square. So write it as a square plus 2ab plus b square. So 3k square plus 2k plus 1. Last term write it as k plus 1. Now expand that series, 2k cube 3k square 2 into 3 6k square, 2 into 3 6k plus 2 plus 3k square plus 6k plus 3 plus k plus 1. After simplification, finally we get the some solution that is equal to, now applying the assumption, let us assume 2k cube plus 3k square plus k equal to 6. Applying that value equal to 6m, 6k square plus k only, 2k square 2k cube. So simply 2k cube plus 3k square plus k, Romani term write it as 6 into 2k square plus 2k plus 1. So this can be written as 6m plus 6 into 2k square plus 2k plus 1, 2k square plus 2k plus 1. Again small rearrangement that above time. So you get the answer is 6 into m plus 6 into m plus 2k square plus 2k plus 1. So that equal to LHS, that equation, 2k plus 1 the whole cube plus 3k plus 1 the whole square plus k plus 1. This is for LHS. So that equal to, that equation is is divisible by 6. Therefore, P of k plus 1 is, for the last term 6 into something values, put k and m is any number. Your final answer will be some multiplication of 6, multiplication in the table of 6. So, the above statement is true for is divisible by 6. So, therefore, assumption P of k equal to k plus 1 is true. The theorem statement and the second statement is so that, so by the induction principle method 2n cube plus 3n square plus n is divisible by 6, hence the theorem. Remaining class will discuss about the topics will be discussed for next class. Next class we discuss about the base B representation problem. Okay, thank you.